Okay, so more of the same, that is, more graphs. So our next example is one that we mentioned before. Y is equal to x to the third plus 5x squared minus 5x minus 10. Now, soon we will deal with how we know how to factor this baby into three pieces, but for right now, I'm sure you'll take my word for it when I tell you that this is equal to y is equal to x plus 5 times x plus 1 times x minus 2. So we have exactly three linear factors for this polynomial of degree 3. Okay, well, so now let's think about graphing it. In the first place, since it is of degree 3, it's got to either go down like that and up like that, the way that x cubed does, or it's going to start high and end low, the way that negative x cubed does. Well, it doesn't have a negative leading coefficient, so we're going to take just the positive alternative. And we have 3 zeros, and we're going to plot the zeros. So I have x equal to negative 5, x equal to negative 1, and x equal to positive 2. And I know that I need to go down like that and up like that, so low on the left, high on the right, simply because this is an odd degree polynomial. Okay, so now I need to go through x equals 5. So I'm coming from below, so I'm going to go like that. Through x equals negative 1. I should examine what the what the y-intercept is. F of 0 is 5 times 1 times negative 2. So when I go through there, I'm going to declare that that's negative 10. You'll notice I have no y scale at all, and we'll talk about why not in a moment. Okay, now, for most polynomials, the quadratic is an exception. I don't know, before I get going, exactly where this max or this min is. But until I get to calculus, I'm not concerned with that. I say again, my main interest is, where is this graph positive? And where is it negative? What's x when it's positive? What's x when it's negative? And also, what's x when it's 0? Okay, so I'm all right with approximating the rest of the shape on this, but we will compare it in a moment with what we see in Desmos, so we'll see that it's actually a pretty decent approximation. Okay, so I know that y is equal to 0 when x is equal to negative 5, negative 1, positive 2. Y is less than 0 when x is less than negative 5, or x is between negative 1 and 2. Okay, now some of you want to know, what if I write it this way? x is in the interval from negative infinity to negative 5, union the interval negative 1 to 2. Well, these are perfectly equivalent, so you can do either one. Okay, and y is greater than 0 when x is between, let's see, that was negative 5 and negative 1, or when x is greater than 2. Okay, so all of these are open intervals. If we put in the endpoints, then we would be including places where x is equal to 0, and that would be an error. Okay, so there's our graph, done just with the knowledge of the end behavior and the zeros. And here's what the graph looks like in Desmos. Notice Desmos has called out these points, negative 5, 0, negative 1, 0, 0, negative 10, and 2, 0. Okay, so this is a pretty decent approximation, I would say. Wouldn't you? Is that a decent approximation? Yeah, it is good enough for our practical purposes. And if anything, we want to be very practical, because time is short and art is very long. Okay, here's a graph that has something different. This is our third example. Y is equal to x minus 2 squared. Okay, now from what we know about transformations, we don't have to worry a whole lot about how to graph it. It's easy. It is a garden variety parabola moved 2 units to the right. Okay, now what this one has that's different is the interesting part here, where the 0 is. This looks like, this is called a vertex or a turning point. And this turning point, with its nose right there on the horizontal axis, has that vertex on the horizontal axis rather than someplace else because of this degree 2. This is called a 0 of multiplicity 2. I often say degree 2 because that makes as much sense to me. Okay, so I call this behavior touch and go. Okay, whenever we have a 0 of even multiplicity, it's going to hit the graph with a touch and go there. Okay, so let's look at one. Our next example is another third degree, or polynomial of degree 3. Y is equal to x plus 1 times x minus 3 squared. Okay, so we have multiplicity 1 for x plus 1 and multiplicity 2 for x minus 3. And if we add up all of the exponents of the linear factors, we get the overall degree. The number of linear factors is the same as the degree of the polynomial. If we multiplied all these things together, we would get x cubed minus 5x squared plus 3x plus 9. But you know what? We are not going to do that unless we absolutely have to. And it isn't any help at all for graphing. So for the time being, we don't need to let that cross our minds. Okay. What is important is that it's a polynomial of degree 3. So, it's going to have end behavior like this around its interesting part. Okay, the interesting part of this one goes like this. At -1, we're going to have a go through. At +3, we're going to have a touch and go. Okay, now I know that it's got a start low on the left and end high on the right because it's of degree 3 and because the leading coefficient is positive. So, to go through, if it starts low like this, it's got to go through like that. If it's coming from somewhere high and needs to do a touch and go and end up high, the touch and go is going to go like that. Now let's find a connector in there. 1 times -3 times -3 gives us a +9. So this y-intercept is at 0, 9. And I'm going to put these together like this. And it's not my best graph ever, I admit. But I can clean that up. And in the meantime, I still have enough information to know this, that y is equal to 0 for x equal to -1 or x equal to 3. Y is less than 0 for x equal, no, not equal, x less than -1. Y is greater than 0 for x between -1 and 3, or x greater than 3. Okay, now I want you to notice I'm talking open intervals here. Three is not included when I'm talking about where y is greater than 0, because at 3, when x is equal to 3, y is equal to 0. We'd better end this one here. So there will be one more part to this video.